in favor of a Darwinian hypothesis. But it leads to the next step in the richening and development of a scientific theory. It leads to the first attempt to put a quantitative number on this. And any attempt to put a quantitative number should induce a profound sense of perplexity, because the number of changes are so much greater than anything we see in the transitional record. Now, what is the proper explanation for this? Please understand, I don't have it. But neither do the other guys. Neither do the other guys. And in my opinion, they refuse to recognize the legitimacy of the question. That is a fundamental question in paleontology. How many changes are required? Can those changes be compared to the fossil record? And if they are compared to the fossil record, why do we see such deficiencies in the record as compared to the necessary changes? Very important issues. The interesting argument about the whale, which is a mammal after all, it belongs to the same group of organisms as a dog, a human being, a chimpanzee, or a tiger. The interesting argument about a whale is that if its origins were land-based originally, then we have some crude way of assessing quantitatively, not qualitatively, but quantitatively, the scope of the project of transformation. The project is very simple. Let's put it in vividly accessible terms. You've got a cow. You want to teach it how to live all of its life in the open ocean, still retaining its air-breathing characteristics. What do you have to do from an engineering point of view to change the cow into a whale? This is crude, but it gives you the essential idea. Now, if the same question were raised with respect to a car, and you ask what would it take to change a car into a submarine, we would understand immediately it would take a great many changes. The project is a massive engineering project of redesign and adaptation. Well, the same question occurs with respect to that proverbial cow. Virtually every feature of the cow has to be changed. It has to be adapted. But since we know that life on Earth and life in the water are fundamentally different enterprises, we have some sense of the number of changes. Anytime a science avoids coming to grips with numbers, it's somehow immersing itself in perhaps an unavoidable, but certainly an unattractive miasma. Here's a chance actually to put some numbers on calculations. We're not talking about genetics. We're talking about simple numbers. The skin has to change completely. It has to become impermeable to water. That's one change. Breathing apparatus has to change. A diving apparatus has to be put in place. Lactation systems have to be designed. The eyes have to be protected. The hearing has to be altered. Salivary organs have to be changed. Feeding mechanisms have to be changed. After all, a cow eats grass, a whale doesn't. As I say, I've tried to do some of these calculations. The calculations are certainly not hard. But they're interesting because I stopped at 50,000. That is morphological changes. And don't forget, these changes are not independent. They're all linked. If you change an organism's visual system, you have to change a great many parts of its cerebellum, its cerebrum, its nervous system. All of these changes are coordinated. So when we're talking about an evolutionary sequence such as this, what's interesting about the cow to whale transition, and I'm just using this as a easily accessible idea. What's interesting about the cow to whale transition is that we can see a different environment is going to impose severe design constraints on a possible evolutionary sequence. How are these constraints met? If they're roughly 50,000. If they're 2 million constraints, how are those met? And what does this suggest about what we should see in the fossil record? To my way of thinking, if Darwinian hypotheses are correct, it should suggest an enormous plethora of animals, intermediary between, say, Ambulocetus and the next step. That won't solve all problems. One wants to know what's directing this change, if anything. But at least it will put it in the ballpark of a quantitative estimate, which is hardly ever done. Questions about homology are really tricky because they tend to be exercises in circular definition. What do we mean by homological organs? Well, in the 19th century, in the early 20th century, geneticists and biologists struggled to put together a criteria for homology. They talked about similarity in embryological development, similarity in function, similarity in morphological form. That's reasonable, but a little vague, a little unclear. But what inference do you make from the fact that, say, the fin in a fish is structured in a way that's remarkably similar to the hand in a human or in a chimpanzee? If the fact that you see some morphological significance is taken as evidence for common descent, there's not much additional that you need to look for by way of evidence because the issue is definitional. If it's not taken as evidence for common descent, what do you need to complete the inference to common descent? There are plenty of examples of homological structures in biology which are obviously not based on common descent. For example, there's an entire family of placental animals in Australia. So, take the Australian wolf, which, except for the reproductive system, features a wide variety of organ systems that are absolutely homological to the North American timber wolf. But there's no evidence that these homological structures arose because some wolf at some time in the past, or some proto-wolf, decided first to migrate to Australia and then to migrate to North America. The evolutionary lines are completely distinct, and yet we see a profound degree of homology. We see this throughout the animal kingdom. The whole issue of homology, commonality of form, is riddled with a great deal of philosophical uncertainty because it's never clear what the evidence is for, and how one is to avoid completely circular reasoning. What is clear is that within family groupings there are profound similarities in structure. We can say that. But whether they arise because of some constraints in the circumstances of life, or because there's a genuine explanation in terms of a common ancestor, we just don't know in many cases. The entire mammalian group of animals, for example, all of the mammals, have many, many properties in common. Why this should be, we don't know. For example, the pentapod nature of all extremities. Why is 5 preferred in the mammalian kingdom and not 7 or 13 or 52? It's an obviously interesting question. If we say that it is because the mammalian organisms were derived ultimately from fish, then we have a profound number of problems in that pectoral and pelvic girdles also obey the rule of 5. They also obey the rule of 5. Where did this constraint come from? It's not entirely clear. The idea that mutations are considered the engines of evolution has only one problem. There's no evidence to support it. As far as we know, and that's a considerable problem, not an overwhelming problem for a scientific theory. There are plenty of scientific theories that lasted a long time with absolutely no evidence. But the idea that mutations are the driving force encounters a fatal difficulties. Almost all mutations are deleterious. Almost all of them do the organism absolutely no good. In fact, we have a devilishly hard time finding any mutations that do the organism any good whatsoever. That's one problem. The second problem is that by now we should be attentive enough to look for contrived circumstances in which we can test this idea that mutations, by definition random, work as the engine of evolution. What we have are a variety of lifelike systems, books, for example, or computer codes. And what we know is that unless we do a lot of careful stage management, arbitrary events in either books or computer codes tend to screw the code of the book up irreparably. Now there's a large question here. If I take a copy of Windows 2000 XP and I start introducing random changes, within a very short while the code will crash. The whole system will be useless. Why exactly is this not happening in living systems? I don't want a lot of hand-waving in response. I want a precise quantitative answer. Living systems don't experience catastrophic failure under random mutations because. And if you know, tell me. I'll take your call day or night.